You can start.
In January, at the end of January 1913, a letter written by Ramanujan reached the Cambridge mathematician Hardy. This letter led to Ramanujan getting world recognition, and in a very short period of time he became a Fellow of the Royal Society and a Fellow of Trinity College, Cambridge. His contributions to mathematics were extraordinary. What I will do now is look at one rather unusual item in the letter written by Ramanujan to Hardy. And this is the following. Now this equation seems absurd. That dot 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 means it does not stop. You go 1 plus 2 plus 3 plus 4 plus 5, never stops. And what Ramanujan was saying, that if you think of this in a particular way, the answer is negative. Each term is positive, but the final answer has to be negative, and its precise number is minus 1 by 12. In all the things Ramanujan did, he had an instinct for making contact with deep results of mathematics. Here, this was also true. To understand this result, there were certain techniques which were necessary, which Ramanujan didn't have at that time. And these techniques involved introducing complex numbers. So a real number is like 1, 2, 3, or a fraction. These are real numbers. A complex number is a pair of real numbers joined together in a particular way. What Ramanujan's result mirrored was some astonishing features present when you think of the series is written using the idea of complex numbers. So let me write down the object which lies behind this. And this is zeta of S is so this is called the Riemann zeta function. And S is complex. So S is equal to x plus iy, where I squared is minus 1. It turns out that this object, because it is complex, there's a way in which you can look at what he's done here. So Ramanujan's result is equal to zeta of minus 1. If I put minus 1, I get 2, minus 1, I get 3. So what Ramanujan intuitively felt that there was some structure, and in this structure, this absurd result, one could make sense out of these. It turns out that this Riemann zeta function is a way in which the distribution of prime numbers can be studied. So Ramanujan's instinct made him intuitively realize that this absurd result depended on some deep structure in mathematics which he didn't know technically, but which he could intuitively sense. Now let me give you an example where you have a sum of positive things can give you a negative answer. If I write 1 plus x squared plus x to the power of n, this is a geometric series, Sn of x. Right? Then we know that this is equal to 1 minus x to the power of n plus 1 over 1 minus x. And x is less than 1. So if I make n become very large, this becomes 1 upon 1 minus x, because the error will be very small. The x is say half to the power of 1 million is going to be very small. Right? So what you find is this object, which is valid for x less than 1, if you add up to infinity, gives you this result. Okay? But this result is also true if in this result I put x equal to 2. There's no problem here. This is then 1 upon 1 minus 2. This is minus 1. So you have something which has only positive terms. You're extending it to outside its range, right? But you can do it after you've carried out the summation. And once you've carried out the summation, if this whole thing for x equal to 2 is minus 1. It turns out that you can also show this by using, instead of x, 1 upon x as the expansion parameter, and you will also get something which is negative. So what we find here is just by looking at something, right, one cannot guess what are the possibilities. Okay? So that's an example. Now what I want to do is to show that this Ramanujan's result can be used in quantum physics to predict a certain kind of force which is called the Casimir force. So I have to state some results, and then you will see that I will get the 1 plus 2 plus that expression. So the first thing is, if I have a string of length L, then it can oscillate like this, or it can go like this, or it can go like this. These are different oscillations of the string. Okay? So this thing is one wavelength. This is L. So this is L over 2. This is L over 2 multiplied by 3. In general, what you have is the wavelength will be n L over 2. N is equal to 1, 2, like this. Okay? Now, wavelength lambda. Okay? Now, you have the following result, that lambda n into nu n is equal to c. That means that if I have an oscillation and there are that many oscillations per second, then the disturbance moves a distance c. So the speed with which the oscillation goes is the product of these two factors. So from here, and C is fixed, so nu n is equal to C over lambda n, and lambda n is this object, so it's lambda n is like this, so lambda n is C n over 2L. Okay? So the frequency is this, and so this is, sorry, it should be 1 by n. You get smaller and smaller. Right? So this is, right? Yeah. So what you find is that this thing is C into n, and where n is equal to 1, 2, like that. Okay? Now, in quantum theory, you have the following result. That's the only thing I would use. In quantum theory, it tells you that if there is a frequency nu, then the system has energy h into nu, where this is Planck's constant. Okay. So that means that for each of these, the energy for En is h into C over L into 2 into N. N is equal to 1, 2, like that. Okay? So for each oscillation wave, there is a corresponding energy. So the total energy, E total, is summation over n, 1 to infinity En, which is equal to 2h over C into L into 1 plus 2 plus 3 plus dot dot, which is exactly the result which Ramanujan had written down. So the total energy is going to be equal to C, and it's half of this. This is a half. Right? So what you have is then H over C L into minus 1 by 12. Okay? So what does this mean? In any physical system, the energy has to take its lowest value. It has to be as low as possible. So you find that as L becomes smaller, this becomes bigger. That means that the thing will try to shrink. That means that there will be an attractive force which will make the thing shrink. Now this idea is used in the quark model, and it is used in different places of physics. So what we find is that there's this loop. You started off with an absurd looking result. Then the absurd looking result, one argued that there was a way of understanding using ideas of complex variables and an idea which is called analytic continuation, and then it made sense. But then you find that the same kind of idea shows up in a physical system where there is oscillations, and the oscillations have an associated energy which is proportional to n, and once you have the thing proportional to n, then you find that the summation which Ramanujan wrote down is minus 1 by 12, and the minus sign is crucial because the minus sign tells you that the force between the two ends of the string will try to make it smaller. It will attract the two ends. And this is something which people have noticed in many different things. In 1996 onwards, this idea, which is called the Casimir energy or the Casimir force, has been found in many different systems. So it is something which is well known and well studied. So this example is the simplest one-dimensional example. There are more involved examples which are present. So one simple application of Ramanujan's result in physics is in quantum physics. And in quantum physics, you find that there is a prediction. And the prediction is that the two ends of a string, which is oscillating like this, will try to come together, make the string smaller. So I think that gives you an idea that behind the various things Ramanujan did, usually there is some deep idea. And usually the deep idea is a deep idea in mathematics. In this case, the Riemann zeta function. And there's a deep idea of physics application, which is the idea of a force due to what is called zero-point energy. And this is one of the legacies of Ramanujan. It is not his most exciting work, but it is something which one can explain rather easily. Thank you.